Hey guys, this is Professor Janacek, and I would like to talk to you about conservative vector fields. So to begin, we'll let C be a curve that's described by the vector valued function r of t on the interval from a to b. C is called a simple curve if r of t1 is not equal to r of t2 for all t1 less than t2. So as I'm developing this curve, I have a t1, I evaluate r at that t value, and then I move down to t2. When I get to some other t value, the r value is never the same. Okay, we can say our curve is closed if r of a is equal to r of b. Remember, a and b are the endpoints of our interval, meaning the r value is the same at the beginning as it is at the end. Integrals on closed curves have a special notation, so if we're going to integrate over a closed curve, our curve here is c. Notice we have that little notation of that circle before we write our integrand and the differential f dr. Let's take a look at examples of these. A curve that is both simple and closed would look something like that, right? It's simple and closed. It's closed because it comes back around to itself, and it's simple because I never really kind of overlap. It would be not simple and yet still closed if we had something like that. Notice because of that little bit right there, it is no longer a simple curve, but it is still closed. The beginning and the end are the same. Something that is not closed would just be, something along those lines. It's simple. This is simple, right? It doesn't kind of touch itself. It doesn't overlap anywhere, but it is definitely not closed. Something that is not simple and not closed would look more like, something like that. So notice it's not simple because of that spot right here, and then of course it's not closed. Those endpoints don't join up together. All right, so that gives us simple versus simple and closed. Let's also now talk about our regions. Let's let R be a region. It is an open region, and it can be described in R2 or perhaps in R3 space. We'll say that our region is connected if it's possible to connect any 2 points in R by a continuous curve. And that curve also is in R, right? We say that R is simply connected if every closed simple curve, that's referencing the curve up here, every closed simple curve in R can be deformed and then contracted down to a point that is also in R. So let's take a look at what these look like. So if we want something that is connected and simply connected, the region would look something like this. So we're looking now at a region, not just the curve. So any 2 points in here, if I take any 2 points, I can connect them. Okay, and it's simply connected because I could squish all of this down and get it to a single point. Right, that's simply connected. Okay, what if we wanted something that was not connected, but is simply connected? And I get the language is a little funny there. The phrase simply connected does mean something very specific. So if I want to say that it's not connected and yet it's simply connected, that would be something like, something like this, where I had this region along with that region. Notice I can contract it down to a point. In fact, in this case, it would be 2 points. I can contract down each blob down to a single point, and that point is still in R. right? However, I can't connect all of the points. If I have a point here and a point there, I cannot connect them. So it's not connected, but we would still say that it is simply connected because I can deform it, contract it down to a single point, and that point still remains in R. All right, what if I'm looking at something that is connected but not simply connected? Well, connected would have to be one big region, but now I've got maybe a hole in this region. So my whole region here is included except for that little opening there. So notice I can still go from any point to any point. Any point here, I can go to any point. I might have to travel around that hole, but it's still okay. It still works. So it is still connected. But if I try to deform it because of that hole there, I won't be able to deform it down to a single point. It's going to always have that little hole in it. So that would make it not simply connected. All right, what if I want something that's not connected and it's also not simply connected? Well, then we would have perhaps a couple of blobs, but one of the blobs is not simply connected. So our region might look something like this. So that would be not connected and not simply connected. All right, now we can say that a vector field, F, we'll call it conservative. Get this to work. It's conservative on the region if there exists a scalar function phi such that F can be written as the gradient on phi. And we call this function, phi is the potential function. We've heard this word before, but now we can connect it to our definition of conservative. So potential if I can find a potential function for F, then we'll call F conservative. Well, there you go. Enjoy.